All right, so the normal distribution stuff, area left, area right, all that. And I'm going to go ahead and pull up StatCrunch as well in case I want to flip over to that. Let's see here. Go.
As of right now, we just see a white screen.
Yeah, I haven't uploaded it yet. Hold on, just give me a sec.
Okay, no, I
All
just
right.
want to make sure.
Yep. There we go. And do you know how to make that bigger? In the upper left-hand corner is like a magnifying glass. You can make it bigger for yourselves so you can see it. All right, so I'm gonna go to page 3, I think. All right, here we go. All right, can you see that okay?
Yep.
All right, cool. So I'm just gonna look at number 7 here. Hey, Evelyn, how's it going? All right, so this is very typical of, I think this is what you were talking about, Matt, like part A, part B, part C, right? It kept going down. So for part A here, this actually is just a straightforward one, and then we'll do one with central limit theorem. So it says what cutoff value would separate the top, the 2.5% verbs that take the most time to process. So this is what I always encourage everybody to do, is to draw a picture of the scenario. So just draw a normal distribution and just mark what you're trying to find. So if you're using that StatCrunch normal calculator, then you can kind of match the picture, right? I'm going to look for area to the right and 2.5% and find the z-score. And if you do that, it'll be I think that's 1.28. And so, or yeah, 1.29 rounds to better, I guess. So, or I'm sorry, 1.96. Sorry, 1.96 is about, that's what we call the 95th percentile, or 95% middle, which is 2.5% on each tail. So the distance from here, let me draw this, hold on. So from essentially from here to here is 1 point, oh, that's really thick. Let me spin that a little bit. 1.96 standard deviations. So the top 2.5% is about 1.96 standard deviations above the mean. If that's the middle right there, cool. So this is where that normal calculator, we can just play around with it until we find, if they give me the percentage, I can solve for the z-score. If they give me the z-score, it'll give me the percentage. And I would just suggest using the standard normal on that, you know, the zeros in the middle, standard deviation is 1. So is everybody cool how we got this 1.96, or would you like me to show that on StatCrunch calculator?
I'm pretty sure I know how you got it. As far as using the calculator.
Yeah.
But, I mean,
Megan and Evelyn, how about you? Looks like Nicole's joining us too.
Yeah, could you show it on StatCrunch, please?
Yeah, no problem. Let me see here. I'm going to go ahead and share application screen. Here we go. So I'm going to pull up StatCrunch here. And I would encourage you all to do the same if you can get StatCrunch open. So if I'm going to try to find the top 2.5%, I'm just going to click on that one. And if you want a blank one, just go StatCrunch new data table. There we go. Never give me a blank one. So we're not looking at all that. All right. So stat calculators normal. All right. So I want the area to the right. So I want greater than, and I want that area to the right to be 0.025. And I hit compute, and there it is, 1.9599. So we round it to 1.96. So the distance from here to here is 1.96 standard deviations above the mean. That's the cutoff to find the top 2.5%. Is that helpful? I mean, we could also say 0.975 and go the other way below, and there it's the same thing. But that's the cutoff for the top 2.5%. So now that we have that, I'm gonna stop sharing that for right now. Is everybody cool with that? And now I'm going to go back to here, share files. All right, and I think Nicole's in here now too. Yep, Nicole, welcome. And Kim is in here too. All right, we're getting a really good turnout. So we just went through how to find this 1.96 here. And what I would suggest is just writing the z-score formula. And that z-score formula is just z. Oh man, it's thick again. And let's change the color back to, let's go, yeah, blue's fine. All right, so z equals x minus mu over sigma, right? So we know the z now, 1.96. We do not know where that score is, so that's x. We do know the mean is 6, and we do know the standard deviation is 1.24. So now this is like the most algebra we do in this class. We multiply both sides times 1.24, and we get 2.43 equals x minus 6. We add 6 over. So that means the cutoff for the top 2.5% is 8.43. So anything that's 8.43 or above, that would be phone orders, would be in the top. Any phone order that takes more than 8.43% is, or minutes, I'm sorry, is in the top 2.5%. All right, any questions on that part A there? Does that look familiar to ones you had to do on your homework?
Yeah.
Okay. So part B is what's the cutoff to separate 16% of the orders that take the least amount of time. So now you just have to find the bottom 16%, which is 1 standard deviation below the mean, approximately. You could do StatCrunch and probably get it a little more exact, but I'm not that picky about that. You could actually use just the empirical rule like we did in chapter 3 and realize that 1 standard deviation is the cutoff. That's, if you remember this from the empirical rule, that this is 34% right here, and the rest is 16%. So the bottom 16% is just -1 standard deviations below the mean. So it's same thing, multiply both sides by 1.24, add 6. So the cutoff for the bottom, so if a phone order process took 4.76 minutes or less, that would be in the bottom 16%. So A and B are very similar. And then C says what would be to separate the 95% that are in the middle. And we can use this right here because we know it's 2.5% and 2.5%, which is 95 in the middle, 2.5 in each tail. So that's 1.96. So we go 1.96 above or 1.96 below. Obviously, it's the same answer here, right, as we got up there. Those are the same because that was the cutoff, the top 2.5%. And then for the bottom, it's, I think it ended up being, yeah, right here, -2.43. So it's, actually, it was supposed to be 3.56, I think. Not. I think I allowed, if you use the empirical rule, if you just said like -2, I gave it a little bit different credit. I have to look at the solutions video how I did that, but I think I accepted both. Somebody have their calculator handy? Could they take -1.96 times 1.24, and do you get -2.43? I think that's correct. And then if you add 6, you're going to get -3.56, I think. So I think that is the correct answer, not that one. So 95% of the phone calls last between 3.56 minutes and 8.43 minutes. So we could now kind of start talking about, well, if I had a phone call that was less than that or more than that, those would be extreme. Now to add a wrinkle to this, and this is the last section, I could modify this question and say, what's the probability that the average of 10 calls would be more than 8.43 minutes long? Okay, so how about if I draw that picture? So now I'm gonna have an average of 10 calls that are 8.43 minutes. And the average was what, 6? So you kind of draw this picture. So now instead of if we just said one piece of data, it's it's going to be 2.5%. But now if I'm looking at the average for a group, the only difference we do now with this formula is divide it by the square root of n. Now, and this becomes x bar. That's the only difference. Instead of just one piece of data, if we're looking for a mean, then we use x bar, and we have what is the size of each mean? That's the square root of n. And this is that discussion board you did over chapter 6 at the end there. So if we did that, let's see here, 8.43 minus 6, right? 8.43 minus 6 over 1.24 divided by the square root of 10. Can somebody with a calculator help me out here? We know the top is 2.43. 2.43 is in the numerator and the denominator. Can somebody take 1.24 divided by the square root of 10 and type it in the chat for me? I'd really appreciate it. So I have to switch screens here.
So I'm trying to follow along with it with the calculator, and I think I'm getting caught up on how to find the square root of or how to square root a number.
Oh, do you have the square root button in your calculator?
I do. Yeah, I have the scientific calculator.
Yep. So go ahead and hit 1.24 divide 10 square root. I think it matters what kind of calculator you have, and then enter. And what do you get?
Okay.
It should be like point.
Oh,
there it is. Nicole got it. Does everybody jive with that? 0.3921. That looks reasonable to me. Okay, cool. So now take 2.43 divided by 0.3921, and what do you get? Like almost 9, maybe. Yeah, what is that? What's 2.43 divided by 0.3921? Yeah, 6 point. Okay, yep, 6 point. That looks good. 6.2 essentially. So think about that. That is 6.2 standard deviations above normal. That is way off the charts, isn't it? That is rare. So the probability, if this is the scenario where these phone calls do actually last on average of 6 minutes, the probability that I would get 10 calls to average 8.43 minutes or more is essentially 0, because that is the p-value for that. If you draw that way on the tail, that's 6 standard deviations above normal. That's essentially 0. So the probability that would happen by random chance is probably almost nil. And so this will lead us into our next chapter, 7 through 9. I'll just give a little pointing forward to that. So now let's say this is what we think, this phone orders, we've done this data, we've calculated this average, but then I went out and found a sample of 10 and they were 8.43. You'd be like, whoa, that shouldn't have happened. Well, that would tell us maybe what we call the null hypothesis, that the mean was 6. Maybe that's not right. Maybe it's taking more time now. And that's what we'll be able to infer, based on our data. We'll say, you know what, we think it's greater than 8.43 minutes now. And we can back it up with some analysis. This is where we're headed into chapter 7, 8, and 9. But it's the same kind of thinking as we're doing right here. All right, questions on 7. I actually extended 7 to make a part D pretty much. But then if there's not any questions, I'll skip to like problem 10. I think that's similar. Everybody good on that? So I would encourage you to review for this test. Go through these old exams, watch the solutions videos, practice them on your own. In fact, take the 2019 exam and just try it, see how you do, and then look at the answers, okay? And then I'm gonna skip down to, let's see here, where's the Let me go to page 4 here. All right, can you see that okay? So number 9, this is a good one. The amount of snowfall falling in a certain mountain range is normally distributed with an average of 170 inches and a standard deviation of 20. What's the probability a randomly selected year will have the average snowfall above 200 inches? So this is just like what we did in chapter 3. 200 minus 170 divided by 20, it's 1.5 standard deviations above normal. Put that right in your normal calculator. It's about a 6% chance, okay? 6-7% chance. The second part is, what's the probability that the mean of 25 years would have an average above 200? So the only difference is it's the mean of a group. Still, we're looking at 200. The only difference is divide by square root of 25, and now that's 7.5 standard deviations above normal. The probability of that happening is essentially 0. That you would get the average for 25 years to be over 200. Do you see? So Matthew, does that help showing the difference there?
Yeah, the only issue was like trying to use that formula because, like I said, I was looking over this stuff and I couldn't figure out how to put it into StatCrunch because most of the videos they go over the formula itself, but not breaking it down to really simple terms. Because like I said, I really don't understand math that well.
Okay, good. Maybe you missed the video that goes over how to use the normal calculator in StatCrunch. Did you ever watch one on that?
I mean I looked at a couple of them, but most of them go over how to use part A, just not part B of those questions.
Okay.
Because then you have that second mean number that they give you.
I'm gonna go back I'm gonna put a link to a video in here, and you can copy paste it into your browser from week 7, chapter 6, in case you missed this one. Okay.
Okay.
I think, and I'll put it right in the chat here. There you go. I think that will kind of go over how to use the normal calculator on these. So do you see how I mean, would you be okay with finding this 0.0668? Would you know how to do that? Right here.
Yeah, I believe so. Yep.
Yeah. So yeah, you just type in 1.5 area to the right. Boom, there it is. And number 10 is another one very similar to all these. Set of test scores. It says the average is 78 with a standard deviation of 9. Find the percentage of scores that are greater than 87. So again, I like drawing the picture. There's the average, there's 87. Really, I'm trying to find out what percentage are up in here, right? I'm trying to find that. And it's just one standard deviation. And if you type that in, it's 0.1587. I would have accepted 16%. That's because you could just use the empirical rule. It's just one standard deviation, area to the right. That's more exact, but I would allow you to just do it the other way. And then find the percentage between 78 and 87. That's this area right here. You could use the empirical rule and go, oh, I know that's 34%. Or you could use your normal calculator and go, okay, this is 0, this is 1. What areas in? And then you can hit the between button on StatCrunch, and it would give you that. So that one tends to maybe be a little easier than 9. Part of that is anyway. And then this is, again, what would be the cutoff for the bottom 10%? So use your normal calculator, find the cutoff for the bottom 10%, and that's negative 1.28. And it's just like the one we did on 7. We know the z-score, we don't know the score, we know the mean, we know the standard deviation. Multiply by 9, add 78, and there we are. So 66.48 would be the cutoff for the bottom 10% of test scores if they're normally distributed. And now the last one is what we just talked about. What's the probability that the mean of 16 students would be over 87? So it's really the same thing as this, except for divide by the square root of, how many is it? 16, which is 4. So now it's just 9 divided by 2.25. You take 9 divided by the square root of 16, and that's So you get 4. And if you're 4 standard deviations above the mean, that's way, I mean, 3 standard deviations is 0.001 or something. So definitely off the charts. Probably if that happening is not going to happen, that you would have the average of a 16-person class to be over 87. All right, so there's 3, I would say, pretty good examples that I just went through. So Matthew, do you have a specific one from your homework on chapter 6 that you would like me that we could do real quick, or how are you feeling on this?
I think you definitely explained it a lot better than some of the other videos. So I will,
Okay.
I'll probably practice it on those 2 because like I said, I only had the 2 that I only got like half points for because I couldn't figure out part B.
Okay.
So I'll go ahead and
Well, if you hit that Ask My Instructor, and I can and I might be able to just tell what error you might be making just by looking at it.
Okay, I'll go ahead and pull it up real quick.
Yeah, if you want to send those. While you're doing that, I'll just go down the list here and see what other questions people have. That's all right.
Yeah.
So I'm going to go with Evelyn's on the top of my list. So Evelyn, how about you? What are you working on? And do you have any questions about discussion, the homework, this test coming up?
Yeah, I had a question on 6.3, question 4.
Okay. You want to shoot that to me through Ask My Instructor?
Yeah.
Thank you. Pull that one up then.
That is also one of the ones I had an issue with. So this will
Okay.
Perfect.
Awesome. I'll look for that to come through here. Let's see here. Kim, how about you? While Evelyn's pulling that up and sending that to me, do you have another one you'd like to look at, or something you're working on? I don't know if she can hear me or not. All right, thank you, Evelyn. I got it. Let me pull this up. Oh yeah, I talked to somebody on the phone about this one the other day. So this is let me see here, 47, 34, 29, and 19. Let me share my screen and we can talk through this one. This one's a little tricky, but I think after you see it, it's not very too crazy anyway. Can you see that? So imagine, okay, so here's the idea they're trying to teach you. If we could sample the entire population, which we can't because we can never get a hold of the whole population, but hypothetically, if we did have every piece of data in a population and then we compared it with samples, all the possible samples that we could take from that population, and we compared them, we're going to find out that the samples will be, the average of the samples will be the same as the actual population mean, which gives us confidence that when we sample, we're getting a very good picture of what the population, what's going on with the population. So what they're doing here is saying, hey, we've got essentially the whole population is these 4 numbers. That's all the data. So if I randomly pick out 2, what are the different things that could happen? So I could pick one out, and let's say I got 47, and then I pick again, and I get 47. What's the average? The average is 47. Now, there's 16 different samples that could be taken from these 4 numbers. For instance, 47, 47, 47, 34, 47, 29, 47, 19, 34, 20, right? So we could list them, and then you can reverse the order because a different one could be like 34, 47. There are 16 different samples that could be drawn from these 4 numbers. The question is, how many of those samples have an average of 47? And that is only 1, because there's only one way that can happen, 47, 47. Now, how about 40.5? Well, that's the average between 47 and 34. So one way, if I sampled and I got 47, I sampled again, I get 34. Or another way I could do it is 34 and then 47. So now there are 2 ways out of 16 that you could get this to be the average of your sample. And then 38, the only way that can, again, that's 2 different ways. 34 is only one way, because the only way I could get an average of 34 is if I went 34, 34. That's the only way that it works here. So that's why it's only 1 out of 16. So really 47, 34, 29, and 19 end up being your 4 that have 1. And all the other ones are going to be 2 out of 16, not 19. So how are we doing so far? Let's see if I get a chat here. I'll come back to that. So these are all the different things. Now, remember how to find the expected value of something? This is a frequency distribution. This is from chapter 2, actually, I think, and 4, maybe. So what we do is we take the value times its probability and get that number, take the value times its probability, get that number, and then we add them all up. And that's how we're going to get 32.25. So if I take 47 times 1/16 plus 40.5 times 2/16 plus 38 times 2/16 plus 34 times 1/16, if we do that for all of these, you get an average of 32.25 if you add them all up. And the average of these 4 numbers is also 32.25. So it shows you that if I take the average of all the possible samples, it will equal the average of the population. That's what they're trying to teach you there. In a kind of cumbersome way, but kind of cool, because it shows, regardless of the population, if we found all the possible samples of size 2 from that population and averaged all of them, it would be exactly the same as the population average.
Is the most efficient way to do that to be like writing it all out and making a table and doing all that, or is there a way to do that like through StatCrunch? Or
Nope, the
Okay.
most efficient way is to just brute force it.
Okay, I just wanted
Yeah,
to make
this is
sure I
more-
wasn't taking an absurd amount of time to do it for no reason.
Well, now that I've explained the shortcut essentially and
Yeah.
recognized, oh, the only way I could get 47, there's only one way. The only way I could get 34, there's only one way. And all the other ones, are 2, and boom, there you go. But yeah, you could put this in StatCrunch and deal with the frequency, but it actually take you more time to get the data into StatCrunch than it would just to calculate it, multiply and add.
Yeah, that doesn't bother me. I just, like, in the first couple chapters, there were times where I realized I was working out problems that I could have just done in StatCrunch, and it was
Yes.
taking me forever. And so I just wanted to make sure
This
this
is-
wasn't that scenario all over again.
Very good thinking, but no, this one's a brute force one. They got to be mean to you sometimes, don't they? You're like, no, my stat lab's mean to me all the time. It's kind of nice. It's like us versus my stat lab. I'm on your side. All right, that was a great question, Matt. Is that what you had too?
Yeah, I was just getting those charts down. I didn't really know how to find the different numbers besides having that second equation, I guess.
Yeah. So as far as how to get, like, does that make sense? How to find the different samples of 2? There's 16 different ways,
Mm-hmm.
and you're just counting them. The average, you just multiply the probability times the value. Do that for all of them, and then add them up, and you'll get that 32.25. Or whatever. Everybody's got a little different example, I think, for theirs, but that's a conceptual question. But yeah, it's a good problem to. I think it's a good. I've taught it many times. It's a good problem to do in class like this. So we can think about, oh wow, the mean, the average of the samples is the same as the mean of the population. So that's great. All right, thank you for that question, Evelyn. Kim, I'll go back to you now. Can you hear me okay? Or you can chat in if you haven't any. Yep. Did you have any questions that you're working on?
Yes. I just don't know exactly what the generates a symbol distribution because when I see on the symboling distribution, I don't know where for set up the generate is a symbol distribution. On this I don't see.
Are you talking about the discussion?
Yeah.
And oh, the applet wasn't working for you? Is that what you're talking about?
Yeah.
It wasn't like you couldn't see the data and all that stuff. Are you using Google Chrome?
Yes.
So how about could you share? Can you pull it up on your computer and show me the error that's happening? And I could have you share your screen back to us, and I could look at it, or I could help you troubleshoot that maybe.
Oh, I don't know how to say.
I have to allow it, but can you pull it up on your computer and then I'll share it back to you? How's that?
Yeah, I will take the picture on the screen and I will send you for email. Dạ đó hả?
Well, how about if you're willing to stick on later, then we could work on it one-on-one if you'd like.
Yeah.
For that, if it's just a technical difficulty thing, okay?
Yes.
All right, I will gladly help you with that. All right, how about, let's go to Megan. How about you? What are you working on?
I got through chapters 5 and 6 pretty well, but I'm still having some trouble with chapter 4. I've just never been good with probability, especially 4.3 and 4.4. I was having some trouble with.
Is that the counting one, I think?
Yes, I was having so much
Yes.
trouble with the factorials and all that, and there was one question that was really confusing.
Do you use the permutations and combinations button on your calculator?
No, I don't think I've ever tried it before, which is probably why I was having trouble.
Yeah, because it's a lot easier just to put, like, I've got a group of 10 and I want to pick a committee of 4, 10C4. That's all the different ways you could do that. So another way you can do it is, I'll show if you're on your computer, I'll show you another, if you don't have in your calculator, if you just on the internet and you want to figure out how to do this, I'll show this, okay? So I go to wolframalpha.com and it'll automatically do, like, I want to do 10 combinations of 4, right? How many different ways could I arrange or make a group of 4 out of 10 things? So all I have to do is go 10C4, boom. Answer is right there, 210. So there's 210 different, like, committees of 4 that you can make out of 10 people. Cool, 210 unique committees. Now, what if I was going to do one, like, I want president, vice president, secretary, treasurer. Now, the order matters then, doesn't it? And if order matters, we use permutations. So now let's put P. And how many different permutations are there? 5,040 permutations. If I had 10 things to choose from, how many different orders of 4 groups that matter? There's 5,040. So have you been using permutations and combinations for that counting stuff?
Yeah, it was a while ago though.
Yeah, that was back that was a few weeks ago. What I'd like to do is actually take you to the test and kind of show you what you really need to know for the exam from chapter 4 and 5. Would that be okay?
Yes.
All right, so I'm going to go ahead and pull that exam back up.
Hey, Professor. Sorry, this is
Yeah.
Nicole. I don't want to interrupt. I have to run to a therapy appointment.
Okay.
But I was just going to let you know this is the exact thing that I had a question over.
Oh,
So
cool.
if you send out the recording later, I'll watch it. And yeah, this is chapter 4 was a beast for me. So anything you can go over on that is what I have a question on too. So
All right. Yep. I'm recording, so I'll post it later.
all right, yeah, solidarity, Megan. All right, thank you.
You bet. All right. So probability is conceptually is important, but doing these mechanical kind of problems is not as important. Okay. We want you to conceptually understand if something is rare or not rare, or how to find the probability of something happening and then determine if it's rare or not rare. So there's only a few problems on your chapter 4 through 6 test, and I almost always have one like this. I just give you a table of data and I ask you a bunch of questions over it. So it's what it does is it allows you to just do basic probability, conditional probability, and then an or scenario. So I'll just go through this really quick. It just like, here's this table. It says, what's the probability that an employee chose online training? All right, how many chose online? It looks like there was, let me get my pointer out, 102, correct? People that chose online out of 136, about 75%, pretty straightforward. So a lot of it is, can you look at this data table and find some basic probabilities? If I asked you, out of the operations people, how many chose traditional? 8 out of 52, something like that. On part B, it's asking what's the probability that an employee chose online training or was involved with quality. So this is both groups, that they chose online or quality. So how many was online? That was 102 out of 136. How many were involved with quality? That's 33 out of 136. But when we did that, we counted these people right here twice, because they were part of the online group and part of the quality group. So if you look at your formula sheet, it's the probability of A plus the probability of B minus the probability of their intersection, or both. So what's the probability that they were both online and quality? So we had to, since those 23 got counted twice, we have to take it out once, and that's how we get this 0.82. Does that seem familiar? Probability of A or B is probability of A plus probability of B minus the intersection. That's if there's overlap, obviously, and there is here. All right, cool, thank you. And then C is when we start talking about conditional probability. That's pretty much what we're just going to restrict. Well, not C yet, but D is. What's the probability that an employee is in the quality division and chose online? So how many were in both? 23. They were in quality and online, 23 out of how many? 136. So really, you're just trying to find out success over total. Success over total. That's what all probability is. Now D gets a little different because it uses this word here, given. That's a conditional. So what's the probability that an employer chose online training given that he or she is in the same division? So if it's probability, if you look at your formula sheet, probability of A given B is the probability of A and B divided by the probability of B. Okay, what the heck does that mean then? Well, the probability of A and B, which we just did, right? The probability that online training and sales, how many is that? There it is, 35. So you can write this a couple different ways. And I like a shortcut method, but it's fine. 35 out of 136. But now I'm only going to compare it with the second thing, which is in the sales division. So if we look at sales, the probability of B is 51 out of 136. But really, it ends up just being 35 out of 51. So instead of doing this kind of, say, more cumbersome over here, the way I think of it is this. If it's given, I find both. So how many are in both categories? Sales and online. Sales and online. There's 35, they're in both. Boom, put that number down. Given, they're in sales. Well, just tell me how many people are in sales. 51. Boom, done. So if I flip-flop that, what if I says, what's the probability that they're in sales given they did online training? Well, how many are in both? 35. But now if I say given they're in online training, I'm not comparing them to this 51, I'm comparing it to the 102. That would be the difference. So whatever the given part becomes your new group or population you're going to compare to, which is what we do right here. Probability that they're in sales given that they're in online. How many are in both? 35. How many are online? 102. And then it says, based on this table, do you believe the type of training chosen is affected by what division they are in? Yes, because they aren't all the same proportion. You can just take any example and show that they're not the same. Or just, yeah, they don't have the same proportion that all choose online and traditional. All right, questions on number 1 there. Does that help you feel a little bit better about part of this probability stuff? There's more, but I just wanted to start with that one. So if I gave you a table, oh yeah, how to get the 102? That is how it says given they're in online. How many people are in online? Right there, 102. Given they're online, we only look at the online people. Cool. Yes. So and there's an example like this I think on every exam. So I would just try one and then watch the solutions video and see if you can get it that way. So those are pretty straightforward. Those are very consistent from year to year. Now 2 is one of those counting ones. Essentially, if I got 20 players, how many teams of 5 could I make? Well, and I want the one that is the tallest. Well, there's only one team that is the tallest. That's why the success, there's only one. There's only one team that would include the tallest. But how many different teams are there? 20C5, which is just like what we did on that permutations combinations example. And then I'll go to the second page here. Now this one's the lottery, and this one's, well, when you play the lottery, does it matter what number or what order the numbers are in? Usually, no. So it says, what if the order did matter? So really it's just 35P5 is this huge number. But if it's order doesn't matter, it's 35C. So I'll just write that on there. So this denominator here is 35P5. And this denominator here is 35 combinations of 5. There's only one that are the winners. So questions on 2 or 3. So hopefully if you just kind of know, or if order matters, it's permutations. If order does not matter, it's combinations. Those are pretty straightforward. Yeah. Now the lottery ones can get more tricky, especially in your online homework. I just give you a basic one because like if we had this one right here, you have to pick the 5 numbers right and the Powerball. Okay, now if there's a Powerball and there's like 50 numbers for Powerball, then you have to take this times 1 out of 50 because you need to get all of these right and get the Powerball, which makes it a lot harder. And then that would be 1 out of whatever that number is there. So if it's an and, we multiply. If it's an or, we add. So those are, but that's about as tough as we get with that particular ones, the counting ones. I don't get too crazy on that. And then number 4 and 5 here are kind of the last types of problems I usually ask. Basic probability, if 70% use full service brokerage and 30% trade in stocks online and 20% do both, if we drew a little Venn diagram of that, we could do that. We know that there's 0.2 here in the middle. And if this is the full service, that means this is 0.5, for it gives you a total of 0.7. And then this would be like 0.1, right? So what's the probability if they do one or the other? What's the probability of A plus the probability of B minus their intersection? And that's how we get 0.8. So 0.7 times 0.3 minus 0.2, because that's the overlaps and I counted twice. If I randomly pick 2 in a row, what's the probability that both of them trade in stocks? So trade in stocks is 30%, and I want it to happen again, 30 and 30 multiplying, there's a 9% chance. And then 4C is the tricky one. This is the binomial probability formula. This is what you did in chapter 5. Because they're saying if 5 investors are selected, what's the probability that exactly 3 of them use a full brokerage firm? So we have a scenario here. It's a yes or no. There's only 2 options. Did they use it or not? Are there different ways this could happen? The answer is yes. If I've got 5 investors and I want 3 of them to use full service, I could go yes, 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 no, no. Or I could go yes, yes, no, yes, no. Or I could go yes. You get the idea. You could, so how many different ways could that happen? Well, that's 5C3. That counts all the different ways it could happen. And what's the probability of that exact thing happening? Well, if 70% of them are, so that's P, and I want exactly 3. So these numbers are always the same. So I'll write the formula here. N, C, R, P to the R, and then 1 minus P. The rest that it doesn't happen would be N minus R. So that's why we get this 3 is right here. So we went 3 successes and 2 failures, exactly. So that's 5 minus 3 is 2. So this is 0.7 times 0.7 times 0.7 times 0.3 times 0.3. That would be the probability of getting one of those occurrences. And then this takes into account how many different combinations that could happen. That's how you do the binomial probability formula. You could also just use StatCrunch and use a binomial calculator like you did on your chapter 5 discussion board. You just type in 0.7 for your success. You type in N is 5. The number of occurrences is exactly 3, and it would give it to you just like that. You can use a binomial calculator as well, or you can use a formula. And that is, I think, then this is the probability distribution. But I'm gonna, before I do that, on problem 4, what are you thinking? And I mean, I guess the good thing is I'm gonna limit the types of questions I'm gonna ask you. They'll be similar to the ones you're seeing on these old exams. Let's see here. And then 5 is just okay, cool. Yep, that's so you get this whole week to review. Test doesn't need to be done until next Tuesday. So I would take serious time, go through many exams, go through your homework problems that you struggled with, feel really good, take a practice, run through a practice exam, and then sit down and take it when you're fresh. There's no rush. The next chapter stuff is when it really amps up in 7 through 9, but we have spring break coming up that next week. So really you have 2 weeks to do the next stuff, but I would suggest getting it done before spring break would be ideal. And then this one is the expected value of this is very similar to the one we did earlier. You just take the value times its probability. So notice 0 times 0.25 is 0, 1 times 0.15, 2 times 0.25, 3 times 0.25. So and you add them all up. So the average is 1.8 successes. So what's the average number of claims every day? 1.8. And if it costs if the average claim costs 5,000, you just take 5,000 times 1.8. It's going to cost $9,000 per day. Throw up in 250 days a year. That's $2.25 million. And if there's 10,000 policyholders, how much does everybody have to pay? You just divide it by 10,000. And so you need to charge all the policyholders at least $225 just to break even. If you charge them more, then you get profit. And that's assuming all of this is accurate. This is a very simplified version, but this is kind of what actuaries do. They don't have typically a specific number, but they have a range based on risk and a high and low range, and then they can say how much risk do we want to assume, how much profit do we need. This is how insurance companies come up with their prices. And I think that's it. Oh, is there one more? Oh, there's one more probability one. Sorry, number 6. And this one is a complementary events. So what's the probability that this is an internet service provider? It looks like 60% of these are resolved within 1 hour. It says out of the next 5 customer calls, they're saying what's the probability that exactly 5 will resolve within 1 hour? Well, that's 0.6 and 0.6 and 0.6 and 0.6, right? So 0.6 to the 5th. So it's about a 7% chance that that would happen. What's probably that at least 1 will be resolved? So this is the complementary event. You could do this. You could say at least 1 will be resolved within an hour. That's 1 or 2 or 3 or 4 or 5. And you can find all of those probabilities, add them all up, which is can be done, but it's a pain. An easier way, say, okay, what's the only thing that doesn't satisfy that? The only thing that does not satisfy that is that nobody gets their service restored within an hour. So we just find 1 minus the probability of the opposite. And the opposite is nobody gets it done. And that's called the complement. So that has to happen 5 times in a row. And the probability of that happening is 40%. So 40% of the time it does not get resolved. So 1 minus 0.4 to the 5th, which is no, 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 no. So that means about 99% of the time, there's going to be at least one of those service calls that is going to get done in an hour. So it's pretty probable. How many would you expect? Mean of a distribution is just the probability times n. So on average, 3 out of 5 calls will be done within an hour. And then what's the probability that none of them would be? And that's really the same thing in here. It's about 1% chance. Okay, so there's all the types of problems I give you. And as you can see, the test is weighted. Chapter 4 and 5 combined, are probably 40 to 50% of the exam. And then chapter 6 is worth much more. It's worth half the exam or more. All right, so I kind of blasted through a whole bunch of problems there. I don't know how helpful, but I hope it narrows your focus into the types of problems you need to practice. And if you go through old exams, you'll probably have enough examples to practice. And then you can go back to your online homework and find ones that you maybe struggled with as well. All right, so I'm gonna just open it up now. Megan, Evelyn, or Matthew, any of you 3, what else would you like to talk about, or anything we just did that you'd like me to go over again?
I sent you the problem with stat, or the I think it was 6.2.
Yeah, okay, I got it. Yep.
As far as this goes, this was very, very helpful for me because there was a lot of that I was not understanding prior. So
sure, let me so I'm just going to read it, that's okay. Survey found that women's heights are normally distributed with a mean of 63.7 and a standard deviation of 2.2 in a certain branch of the military. They have to be between 58 and 80 inches. So find the probability that they're too tall or too short. You probably did that one fine, didn't you? Is that right, Matt? The part A?
yeah, part A is, yeah, I was
Yep.
able to get that.
So now on part B, it says, if this branch is going to change its requirements, so it's just the bottom 1% and the top 2% are cut out. Now what's the height requirements? So let's go ahead and I'm going to pull up a whiteboard here. I'm going to put this over here. All right. I'm looking at my other screen. All right. So let's do a whiteboard. Whiteboard. All right. So what I'm going to do is I'm just going to draw a picture to start with. Why they go so. So here's the normal distribution. There's the average. So really what they're saying is I want the bottom 1% and the top 2%, 0.01 and 0.02. Those are the only ones that are not going to get in, right? And the average is 63.7. That's the mean. And the standard deviation is 2.2. Cool. Now, Matt, do you have your StatCrunch open with your normal calculator?
Yes.
Can you use that to find the z-score for the bottom 1%? Tell me what that is. It's gonna be negative something.
So as far as putting it into the calculator, you just use standard, right?
Yep, yep. And so for the after the equal sign, you put the percentage, which is 0.01, shade left, hit enter. What's it give you?
One second here. You said you put it into the equal sign, you put 0.
0.01, yep, yep. Because that's what it gives you, the percentage after the equals, right?
Mm-hmm. It's saying
And then hit solve.
68.81.
What'd you get?
68.81.
Make your mean be 0
Oh, okay.
and your standard deviation be 1. We're just going to use the standard normal. What you're doing is another way to do it, but I'd rather just get you thinking more like the standard normal if I can.
Right, negative 2.32.
Yeah, so I'm going to round to negative 2.33. So this is just like what we did before now. Negative 2. We know the z-score. I don't know what that height is. I do know the mean is 63.7, and I do know the standard deviation is 2.2. So you're able to solve that now, right? And how would you solve this one?
Would you put that negative number into the the equal box then, or with those?
You're trying to isolate x. So how do we do this algebra? We got to get the 63.7 is 2.2 out of there. How do we do that? So that's division. What's the opposite of division?
Multiplication, or
yeah, multiply. Yep. So we're just going to multiply both sides by 2.2. Cool. So type that in your calculator. What's 2.2 times negative 2.33?
the 2.23 or 33?
Yeah, 2.33. Yeah, what do you get?
5.12.
Negative 5.12.
Yes.
All right. Now how do we get x? Now what's the last step here? How do we get x by itself?
You do the same except with 63.7, or?
Yep, it's subtraction. So how do we undo that? What's the opposite of subtraction?
Addition.
Yeah, so we're just going to add 63.7, add 63.7, and there we go. So what does that answer?
So you do 63.7 plus 5.12.
It's a negative, so make sure you make that negative. Yep. Because we're going below average, right?
31.58.
Say that again.
35.18.
Ooh, that seems a lot. It's girls are on average 63.7 inches. I'm only going to take off 5 inches, so that puts me in the 50s.
How did I get that number then?
63.7 minus 5.12 is
58.58.
there you go. So that would be the shortest woman that would be allowed in the military, that branch of the military. And the tallest is the same thing, except we're looking for the top 2%. So again, go to StatCrunch normal calculator, find the z-score for the top 2%. Can you do that quick?
Mm-hmm. Negative 2.5.
It's above normal, so it should be a positive z-score.
Oh, okay. .05.
There you go. Very good. So 2.05 equals, and it's the same problem, right? X minus 63.7 over 2.2, and we know how to solve that. Multiply by 2.2, add 63.7, that will give you your cutoff, and that would be the shortest and the tallest woman that would be allowed. Cool?
Okay. Yeah, that's actually amazing.
All right, Cam, thanks for being here. So that's a really good one to practice right there. Yep. And that's very similar to what we just did on that test too. You know, this is very similar to what you might see in the exam.
Thank you so
And
much.
yeah, I think just keep practicing these. And I like drawing the picture, shading, you know, using your calculator, use the formula, do a little algebra here. And this is the most algebra you're gonna do in this class right here.
That's encouraging to hear then.
Yes, it is. You don't need to do a whole bunch of crazy stuff. Now you could probably cheat a little by using your normal calculator. If you just type the mean to be 63.7 and the standard deviation to be 2.2, why don't you do that really quick? Let the mean be 63.7, standard deviation be 2.2, and then type in 0.01 after the equals and hit enter. And does it give you 58.58?
Sorry, for the mean, do what now?
The mean is 63.7, right?
Yep.
Standard deviation is 2.2. So we're not going to use the standard normal. We're going to use what this is telling us.
Mm-hmm.
And then we know and then 0.01 is the percentage. So that's after the equal sign. Shade to the left. Hit solve, and what do you get?
68.81.
I think that would be the top. I think you want to shade to the left.
Oh, yep.
You want to put 0.01.
58.58.
There it is. See?
How about that?
Why didn't you just do that in the first place? Because I wanted you to learn. Sorry.
Yeah.
But you get how that's. I think you're hopefully getting a sense of what's going on here now.
I do, and that was kind of the thing. I just didn't understand how to. The formula wasn't making sense to me. Like I would go over the example, and I really do appreciate how it does have the examples in the homework, so you could see
Yes.
it, you know, caveman style, but it just wasn't clicking to make sense to me. So that having it on this whiteboard makes a lot more sense.
Yeah. Yep. And this is what, when you look at my solutions for the exams, hopefully you can kind of see how the work plays out like this. You know, you get after you practice a little bit.
Mm-hmm.
All right. Well, this is excellent online office hour. Thank you so much for calling me yesterday and coordinating all this, and I encourage more of that.
Yeah, thank you.
All right. Well, I see Evelyn and Megan are still here. How about either of you, Evelyn or Megan? Do you have a question you'd like to ask?
Yeah, I had a question for 6.4. I emailed it to you.
Oh, I couldn't quite hear you. Can you say that again?
I had a question for 6.4 and I emailed it to you.
Oh, okay. All right. It says the weights of a certain brand of candies are normally distributed, and they give you the mean and they give the standard deviation. A sample of these candies came containing 462 candies, and the package label said that the net weight is 394.5 grams. If every package has 462 candies, the mean weight of the candies must exceed 0.8538, right? If one candy is randomly selected, find the probability that it weighs more than 0.8538. So can you draw a normal distribution? Let's do this on a whiteboard. How's that? I'm going to clear this whiteboard. Get a new one here. Clear. Yes, clear. All right, so this is very similar to what we're doing here. Just draw your normal distribution, right? The average is 0.8615. And they're essentially saying what proportion are heavier than 0.8538. So I'm just gonna put that over here because it's below normal, right? 0.8538. Oh, this is question, this is good 6.4 number 4. 6.4, 6.4 number 4. Cool. So really they're just saying what's the probability that you could pick one candy and it's going to be essentially heavy enough to be on the average that we need to be finding. So that would be this shaded here. You could kind of cheat a little bit on this one. You could just go right to your normal calculator, type in 0.8615 for the mean, type in the standard deviation, which is 0.0515, and then put in 0.853 and shade to the right and enter, and it should give you this number. The other option is to use the z-score and then use the standard normal calculator, which would be 0.8538 minus 0.86, which is 15, is the mean, divided by 0.0515. That'll give you your z-score, find your area to the right, and away you go. And somebody want to do that quick? Does somebody have their normal calculator or their calculator open that can find this? So Evelyn, are you going to use you're going to find the z-score, or are you just going to use StatCrunch normal calculator to find the area? Or both?
I'm trying to do it on StatCrunch.
Okay, cool. So you put 0.8615 in for the mean, right? And 0.0515 for the standard deviation, right? And then your x is going to be 0.8538, and you're going to shade to the right, greater than, and what do you get? So this area here is, I could do it on my computer too here. I will do the same thing. The mean is 0.8615. The standard deviation is 0.0515. And I'm going to go greater than 0.8538 and compute 0.559 essentially. So this is 0.559. Cool. So that'd be the probability of getting 1. But the second part is going to be what's the probability that the bag average is going to be heavy enough. I believe that's going to be part 2. I'll type that number in quick. That was what I'll type it in point, round to 4 decimal places. It says 0.5594. I don't need that many, just 4. Okay, there we go. That's right. 462 candies are randomly selected. Find the probability that their mean weight is at least that. So it's the same problem, except for we are just going to divide by the square root of, is it 462? Yeah, 462. So this is why you need to use your standard normal calculator. So Evelyn, can you do me a favor? Can you take 0.8538 minus 0.8615? What is that number? I'm not sure if you're hearing me, so I'll just do it. 0.8538 minus 0.8615 is negative 0.0077. And now if I take 0.0515 divided by the square root of 462. That is 0.00239. And let's go 6. So now, if I take 0.00, oh yeah, negative, I'm sorry, negative 0.0077 divided by that, I get, make sure I get this right, 0.00239. Yeah. Now, Z equals negative 3.2137. So now if I use my standard, if I use my calculator, I'll put mean of 0, standard deviation of 1. I'm just going to use a standard normal calculator. And I know the z-score is negative 3.2137. Oops, mic's not working. Negative 2.3137. And I want to go greater than and compute. So it's 0.989. So essentially it's 99%. How accurate do they want this to be? 4 decimal places. So that's going to be 0.9896, but it rounds up. So essentially it's going to be 0.9900 to round up 4 decimal places. Oops, maybe I didn't quite. I probably didn't carry enough digits. Let's see here. Let me put a few more digits in. Negative 0.3213689. Try that. Try that. There we go. 0.98. I don't know. Let's see if it likes this. 0.9896. Let's see if it likes that. Nope. Must not be carrying enough digits. I got a feeling I chopped too many out. Darn. That's annoying. Yeah, it was 0.9993. So I was off. Well, 0.99 was off by 3/10,000ths. So sorry about that. I should have carried more digits for my whole calculation. That's good to learn. And then essentially, you almost, I mean, the probability that you would find a bag that's underweight is only what, 7 out of 10,000. So it says, given these results, does it seem that candy companies providing consumers with the amount of, yes, because it's, it is exceptionally small. Ooh. Oh, is that one? Yes, probably getting blah, blah, is selected is yes, because does it seem they are? Yes, because the probability of getting is small. That seems okay. I don't know why they're saying that. Uh-oh, is that an error? Oh, I think they're saying the probability of it getting is not small, it's large. That's stupid. Because with hypothesis testing, we're only looking for the probability of it not being, not the probability that it is being, which is, so that's why I guess they're just using that number. I guess we're not in chapter 7 through 9 yet, so I guess that makes sense. But all right, well, there we go. I think that tells me I'm ready for lunch. Are we, how, is that enough practice for today, or did you guys have another one? That one is a bugger, because they want to carry so many digits.
I think I'm just going to go over these and practice them.
Yep. Well, you got a whole week to work on it. There's no new assignment this week, so if you guys want to do this again, I'd be really up for it. If you want to do it like, if you know you're going to take the test on, I don't know, Monday or Tuesday, if you want to do a little review session before you take it, that'd be great.
I think that'd be good. Yeah, maybe.
Yeah. Just shoot me an email and just request a time. It'll probably work.
Okay.
Cool.
Yeah.
All right. Well, I think I'm gonna go get some lunch. You are welcome, and I'm gonna stop the recording here.